Good morning. I just want to finish up a couple of loose ends from the end of chapter 1 before we move on to chapter 2, which is about initial segments of the universe V. We were talking last time about taking transitive classes of sets and looking at relativizations of formulae to these sets, and whether the truth of a formula relativized to a structure like this about some set X, would it be true in W if and only if it was true in V, for example. If it was, we would call it absolute. But in general, what we're looking at are properties of sets in general in such transitive it might be V, in such transitive chunks that sit inside the universe. And dilemmas at the very end of the chapter say, okay, if the W is sufficiently closed, it's got a sufficient number of sets in it, then it's going to be a model of some of the axioms. For example, what do I mean here? If I've got X and Y here in W, I'm going to assume here W is transitive. So that always means the axiom of extensionality holds. Right? W has all the epsilon facts available to it about its members. So here's X and Y. Now there's nothing about being transitive that means that the pair set X, Y is in there. But suppose it is. So suppose for any X and Y in W, there is this Z in W, such that Z is X and Y. So this declares, actually, that for any two sets, there is this set in W, which is this pair set. And indeed, the Z here truly is the pair set, because W is transitive. It's not that if there is this Z in W, that W thinks is a pair set, and the Z has got some other member lurking outside of W. That can't happen. If Z is in W, it's a subset of W. So we would naturally say, if this happens, that, okay, W is closed under unordered pairs. So actually, we'd want to say the axiom of pair holds inside W. And that is what the lemma 124 justifies. Right? What lemma 124 does is take the expression, the official expression for the axiom of pair here, relativizes it to W, and proves that that must hold for any W, as long as W is transitive, and the supposition holds about W. So it's a natural thing to want to demonstrate. I'm not going to go through the proof because I think it's kind of intuitively obvious from our point of view of developing the axioms here, that if W is closed under this operation, then the axiom of pair, we'll say the axiom of pair holds in W. Though 124 then formally justifies that. Another example is, say, we look at unions. So example 2 at the top of the page at the top of the page. So that said, again, if we've got X in W, again W transitive, then the union of x is the union of x in the sense of W. And if such exists in W. Now, just because x is in here and W is transitive, it doesn't mean that there is a union set of x in W. But if there is, it truly is the union set by the reasoning of the example. If we knew that for every x, we'd be justified in saying the axiom of union held in W. So if for every x in W, there is a z in W, so that z is the union of x in the sense of W. If, then the axiom of union holds in W, which indeed is quite natural. Right? The axiom of union just says, indeed, for any x, there has to be a union set. So the rest of lemma 125, and indeed the lemma 126 afterwards, goes through various properties that W must be closed under for the axiom, when written out in this relativized form, to be provably true in it. So again, another example is the infinity axiom. If omega is an element of W, then the axiom of infinity will hold in W, and we can prove that. And similar reasoning for for the other axioms. So I want to refer back to the statements, or these conditions that are there on W, in order to get certain axioms to hold. We'll need to refer back later on to that. The other loose end I wanted to talk about just relates to the completeness theorem. But let me just first mention a bit of nomenclature. A set of sentences, so without free variables, T say, is sometimes called a theory. Other people say the set of consequences of T, the deducible consequences of T, is the theory. Deducible from T is or the theory. So in particular, if T is ZF, of course, this is what we're thinking about. Some people would say T is the set of axioms of ZF, the theory of ZF is the set of axioms. Other people would say the set of consequences of ZF is the theory. And of course, it's the soundness theorem, the first order logic, that says actually there's no real confusion here. We know that if something is deducible, right, from a theory, then in any structure in which T holds, sigma holds. Yeah. So this is the soundness theorem here. And I can always just, now what the lemma does, or sorry, the theorem does in the notes here, it says, so if W again is a transitive term, So again, meaning defines a transitive collection of sets. So if I take some formula in the language here of set theory, if I can prove this formula here, then it holds in W. So this is a counterpart to saying this here from the soundness theorem. Sigma holds with all its quantifiers relativized to W. So we're justified in saying it's true in this structure W. Yeah. The variation of the theorem says if gamma is finite, and if from gamma I can deduce sigma in first order logic, I can take the conjunction of the, better introduce this notation. What do I mean by this big conjunction symbol at the front here? If gamma is a finite set of formulae, maybe gamma is gamma 0 up to gamma n here, then this big conjunction here of gamma is just defined to be the conjunction of the formulae that make up gamma. And you could see why the requirement is that it's finite, because there's no such thing as an infinite conjunction. All our formulae in our language are finite strings here. So the theorem says if I've got a finite set of formulae here, and if I can prove sigma from gamma, then the conjunction of the formulae in gamma relativized to W, if that holds, I'll know that sigma holds in W. So again, just there's nothing so mysterious here. If I've got the axioms for group theory, right, there's 3 axioms here. If I've got a structure, and if I know that the axioms of group theory hold in the structure, which means it's a group, right, then anything I can deduce from the group theory axioms will hold in the structure. That's the way to think of that theorem there. Okay, fine, that concludes what I wanted to say about chapter 1, and we'll now move on to chapter 2. Okay, so chapter 2 here. So it's entitled Initial Segments of the Universe. So the idea is, it's sort of an overarching title. There are actually many topics here within this chapter. But the idea is that we can investigate initial segments of the universe V, right, in our set theory here. We think of an initial segment of the universe, the sets up to some rank, up to some V alpha, and this is an object of study for us as set theorists. The first part, section 2.1, is actually a standard one talking about cardinal numbers, various properties of cardinal numbers we want to investigate a little more thoroughly than we did in the set theory course. So 2.1 is investigating the notion of cofinality. Cofinality. And the idea is we just look at functions between ordinals is the basic substratum of the discussion here. I take two ordinals. So lowercase Greek denotes ordinals here. Suppose I've got a function from alpha into beta. Here's alpha, and here's beta. And I suppose that beta is a limit ordinal, which I'll write like this. All right, so it's not a successor of something. So I've got this function f, so it's taking the ordinals below alpha here, and it's sending them over to beta here. We'll say that the function is a cofinal function from alpha into beta if the range of the map goes unboundedly high up below beta. Final map into beta. And I'll often write something like cof over the top here for that. And in the text it says the sup of the range of f is beta. So this means you give me any delta here, I can find some tor down here, such that f of tor is bigger than the delta you gave me. So things in the range of f appear all the way up, as high as you can get below the ordinal beta here. So we can succinctly write that as that. Supremum of the range of f is beta here. In other words, I say f is unbounded in beta. And this idea really only makes sense if beta is a limit ordinal here. We don't want to fuss about this kind of aqueous cases when beta is a successor ordinal here. So we want to investigate these properties of ordinals, which, what are cofinal maps like into some particular ordinal beta? Can we find cofinal maps into an ordinal beta always from some smaller ordinal, alpha here? When does that happen, or when does that not happen? So let's look at some examples then. Let's consider the first omega alephs. So here's omega 0 or omega. Here are the finite down here, ordinals here. Now, what comes after the aleph ends is the omega-th infinite cardinal, which we write synonymously over there. Aleph version and this omega subversion here. So we said in the Z theory course that this is the first limit cardinal. It comes after the aleph ends, And it's not a successor. I mean, Aleph 2 is the successor of Aleph 1 as cardinals. Aleph 1 is the successor cardinal of Aleph 0. So Aleph omega is the first limit of these Aleph ends here. So there's an obvious function that we can define. We define f from omega cofinally into Aleph omega, or omega sub omega, here. And I just send k to omega sub k, or Aleph sub k if you prefer. So that is a function whose domain is down here, omega, and it sends things in a nice orderly fashion, increasing fashion up like this. And every Aleph k here is in the range of f, so f is then unbounded in Aleph omega. So this is a cofinal map here. Now I can repeat this idea. I can have G going from omega 1 into Aleph sub omega 1, or if you like, omega sub omega 1. I'm going to use the same picture, except now, up here, I've got Aleph sub omega 1. So there are countably many infinite cardinals before this cardinal. So this is the first cardinal, right, which has got uncountably many cardinals before it. So again, 0 is going to go to Aleph omega. Here's omega. This will go to, let's call this one omega. Yeah, this will go to, no, let's call this one omega down here. So this one will go to Aleph omega, sub omega. Omega plus 1 here will go to Aleph omega plus 1. And then through all of the countable ordinals here, if alpha is countable, this will go up to Aleph alpha. Right. So through all the countable ordinals below omega 1, alpha goes to Aleph alpha. So we define it like this way. So then G is also cofinal in here. Sorry, it's looking a bit crowded. But, so these are examples of cofinal maps where I'm taking a smaller ordinal. I'm thinking now here of omega 1 as an ordinal as well as a cardinal, of course. I'm taking a smaller ordinal and I'm sending it unboundedly into this huge ordinal here. I'm just thinking I'll use the ordinals here to enumerate the cardinals below this Aleph sub omega 1 here. Okay, what's the fourth example? I could define a sequence. Sequence here. F of 0, I take it to be Aleph 0. This function is going to grow very fast. Right? Well, let me spell it out. What is f of 1? Right? That's going to be omega of f of 0, which is omega So actually this is just, in this case, this is just aleph omega, right? It's the omega zeroth aleph. Omega is synonymous with omega sub 0. F of 2 will be omega sub f of 1. Right? We're going to define it as this. So here we've got this. This is the first limit cardinal. And here we've got the cardinal that is this limit cardinal far away in the enumeration of all of the alephs. So this is omega of omega 0. So this is an enormous cardinal. Right? And we'll continue like this. F of n plus 1 will just be omega sub f of n. So this is going to look like you know, omega sub omega sub omega sub omega. I'm not going to put in all of the brackets down here. So it's an increasing function, right? Picking out, leaping ahead, leaping through the enumeration of the cardinals like this. So now I'll just let f of omega, I'll just define it to be, well, let beta be the supremum of all of these f of n's. So here would be the first one, here's f of 0, right, which was just aleph sub omega. Here's f of 1, f of 2, f of 3, f of n. And this is the supremum, which we're calling beta. So by design, the way I've done this, I've designed it that omega is going to be cofinal into beta because I've defined beta to be a limit of these fn's, f0, f1, f2, fn, and so on. So getting rid of this for a moment here. Then again, here I've got now little old omega down here. And this is f of 0, and this is f of 1. And again, there's this increasing function, which grows extremely fast down here. So then again, f is a cofinal function into this beta. By design. And the next example introduces just some notation that we'll need. Suppose I've got a subset of beta. Again, beta is still a limit ordinal. I can just, here's beta. And here's b. So I can just define the enumerating function for b here. So this is b. I'll just enumerate b in increasing order, just using the ordinals. So I'll call this one f of 0. The next one I'll call f of 1. Next one will be f of 2, and so on. So actually, let me write f sub b here. F sub b is a strictly increasing function that enumerates b. In increasing order. Well, I've said that. It's an increasing function. So I just think of this. First element, second element, third element, and so on. So of course, b can have many, many elements in it. If b as a set of ordinals is unbounded in beta, So if the supremum of B is beta, again, supremum, this means that for any ordinal gamma less than beta, there is some delta in B that's above it. So B goes all the way up to the top. Then f of B is cofinal in beta. By design, right? We've specified that B is cofinal, as it were, already in beta. So the enumerating function will, of course, then take some ordinal, which we haven't specified in this diagram. It'll take some ordinal cofinally into beta. So it only needs as many ordinals as it takes to enumerate B. So the order type of the ordinals less than beta is, of course, just beta. So it's not going to take more than beta many ordinals to enumerate B, but it could take less. So it might be that if I take this beta here, it may be possible to find functions from smaller ordinals cofinally into it, as in our previous examples. But then for some beta, that may just simply not be possible. It may not be possible to find a function from a smaller ordinal cofinally into it. So the ordinals, this gives us then a notion, which we can define, of the cofinality of a limit ordinal. This is definition 2.3. Definition 2.2, I'll just let you read, just formalizes this idea of unboundedness, which I've just sketched here on the board here. So this is the important definition for today. The cofinality of a limit ordinal, beta, is the least alpha such that there is some function from alpha going cofinally into beta. So again, here's beta and here's alpha. Of course, there are many functions into beta. We look at the ones whose range is unbounded in beta. There may be many of those, or there will be many of those. But we look for functions where the domain is least. So somehow I think of approximating beta in alpha steps, where alpha is the smallest possible value. So we write this least alpha. Alpha as cof beta, CF beta. So in the examples we gave here, example, I didn't talk about example 1, but examples 1 and 2. The cofinality of beta was omega. Here we had beta was Aleph omega. We had omega here, and we were sending the natural number n up to Aleph n. And it's reasonably obvious that this Aleph omega can't have any smaller cofinality, because a finite number here can't go unboundedly up into this beta here. If I took a smaller possible domain for my f, all it could do is enumerate n things here, and it wouldn't reach up to this limit ordinal. So the cofinality of beta in this case is exactly omega. and the function witnessing it was this one here. In example 3, I reran that, where instead of omega here, we took omega 1. And actually here we had omega 1. And now the same reasoning showed in example 3 the cofinality of beta was omega 1. Here this was beta was aleph omega 1 down here. So these are two examples of, well, cardinals whose cofinality is less than themselves. Cardinals, beta, well, namely this aleph omega and aleph omega 1, where the cofinality of beta is less than beta. It was either omega or omega 1, respectively. So we're going to call a limit ordinal singular if I can approach it from below using a function with a smaller domain. In other words, if its cofinality is less than itself. So definition true form. A limit ordinal beta is singular if cofinality of beta is less than beta. Otherwise, it's called regular. So regular is just not singular. And part 2 of the definition is just some notations. Not so much ideas as notations. So let's just see. We just let reg abbreviate the kappas such that kappa is regular. We're going to let card be the collection of kappa such that kappa is a cardinal. And sing with this capital S here, this will be the kappas that are cardinals but also singular. And we already saw aleph sub omega and aleph sub omega 1. These are singular cardinals here. And lim card, another piece of notation, is just an abbreviation for being a limit cardinal, as opposed to a successor cardinal, like one of the aleph ets. So these are classes of cardinals here. So kappa is a cardinal and kappa is a limit cardinal. Again, like the aleph omega, aleph sub omega plus omega, aleph sub omega plus omega plus omega. Okay. There's a comment that one could define cofinality for successor ordinals, but it becomes rather silly and rather vacuous, so I'm just not bothering to do it here. But I want somewhat to make some observation about regularity and singularity here. And this is lemma 2.5. We'll just make this observation. Cofinality of an ordinal is always less than or equal to the cardinality of the ordinal, which of course is less than the ordinal itself. So why does this observation hold true? What is the cardinality of an ordinal beta? It's the least ordinal where there's a bijection between it and beta. Well, if it's a bijection, it means it's onto. So certainly a bijection between this and this is going to be cofinal into beta because it's onto beta. So if this is the least, being a bijection is a stronger condition than being a cofinal map. So the least ordinal which I can biject with beta is certainly no bigger than beta, but it might be that I could have a function that's unbounded in beta without being a bijection. So I might be able to find a smaller ordinal here than the cardinality, which is unbounded into beta here. So this is just an observation on the definitions of cof and cardinality here. But that allows us then to write down cofinality of beta equals beta. What did this mean? This meant beta was regular. So there's nothing new here. That's what being regular means. Its cofinality is beta. But this is the same as beta being regular and beta a cardinal. Obviously, this implies this, but if beta is regular, it means the cofinality of beta equals beta. So we've sandwiched these two things in here. So the only thing that's up for discussion here is this left arrow's right here. If beta is regular, then cofinality of beta is the same as its cardinality is beta. And that's what it is for beta to be a cardinal. It is its own cardinality. And if it's a regular cardinal, it's its own cofinality as well. But we've seen that there are singular cardinals which have smaller cofinality, as in Aleph Omega. So Hausdorff showed that a successor cardinal, something like an Aleph n, something that's the least cardinal beyond a certain point, these are always regular. So there are plenty of regular cardinals. There are plenty of singular cardinals too. So this notation, I'll write it down, remind you here. Lambda plus This is the least cardinal bigger than lambda. So the successor of any, for example, if lambda is a cardinal, this is the next cardinal. So the successor of any cardinal is always regular. So the argument here uses the fact that if I have lambda many sets of cardinality lambda, then their union has got cardinality at most lambda. So to state it a little bit more mathematically, I've got a sequence of sets here. I've got lambda many sets here. And the cardinality of each of these is less than or equal to lambda. If I take the union of them all, this has got cardinality less than or equal to lambda times lambda, which is lambda. There are lambda many sets, each of which has got size less than or equal to lambda. So this was something from our set theory course, and something that one needs the axiom of choice to prove. So let's just see how the argument of the proof goes, and we'll finish at this point. So what's our assumption? What are we trying to prove? Let's write it up again. Lemma here. Lambda plus is regular for any lambda. So for any infinite cardinal lambda, or for any infinite lambda. So suppose not for a contradiction. If lambda plus is not regular, this says the cofinality of lambda plus is less than lambda plus. So we invoke the definition of what cofinality is. So here will be lambda, here will be lambda plus. So there's a function f from some alpha into lambda plus, which is cofinal. And the crucial point is, I could take alpha to be this cofinality. Alpha is less than lambda plus. I could just say here alpha equals cofinality of lambda plus. But anyway. So what I've got here is an alpha whose cardinality is less than or equal to lambda. Alpha is somewhere or other down here. So here may be alpha, and here I've got this function. going up like this. It doesn't have to be increasing, actually. I've drawn it confusingly, always like that. But now I just think of the ordinals, the images here in the range of F, as being sets, the x's that I had, which I've just rubbed out. But then each F of tau is a set. It would be tau, here's some F of tau, is a set of cardinality, again lambda. Because any of the ordinals less than lambda plus have got cardinality less than or equal to lambda. So the union here of the taus less than alpha, of all of these F of taus here, this has got size less than or equal to lambda. Each of these has got size less than or equal to lambda. So this cardinality here is less than or equal to lambda times lambda, which is lambda. But these, every ordinal that's less than lambda plus is in one of these F taus. Lambda plus is contained in this one. Because F is cofinal here. So this can't have size less than or equal to lambda because it's got size at least that of the next cardinal. So lambda plus is less than or equal to the cardinality of this union. So we've got it simultaneously no bigger than lambda, but actually no smaller than lambda plus. So this is our contradiction. Okay, so bolt of lightning there. So our supposition is that lambda plus was not regular, was false. So that finishes that argument. So successor cardinals then are examples of regular cardinals. Okay, so next time we will look at seeing how we can always assume that our cofinalizing functions are strictly increasing, and we'll start look at some enumerating functions of sets below regular cardinals. Okay, thank you.